Welcome to Lecture 16C, Triple Integrals in Spherical Coordinates, and a set of examples which are a little bit more challenging. Again, this material is covered in section 16.5 of the text, and reading assignment 2, reference material from section 3.2. This is not mandatory reading. The objectives are to understand a select set of more difficult problems from the assigned problems and previous quizzes and exams. And again, the concepts and visualization skills we're dealing with here are the integration bounds for radius rho, angle psi, and angle theta, visualization of bounding surfaces in spherical coordinates, and the differential volume in spherical coordinates. I've got two additional notes here. One is that these examples have already been covered in the lecture before. We looked at some of these examples, if not most of them, in Cartesian coordinates as well as in cylindrical coordinates. But given that we've done those two, we can now basically also look at how you would solve them in spherical coordinates. So it turns out that in many cases, they're much easier to calculate in the coordinate system other than Cartesian. Lecture 16.3 contains worked out examples from the textbook, and you can skip this lecture if you were able to understand the homework examples. Just one caveat that some of these examples I've done in spherical coordinates actually do not exist in the textbook, so they're quite new. So you'll have to pick and choose your way through this lecture as it suits you. Well, as usual, the second slide, just a summary of the slides to follow, and that will be the three specific problems that I've extracted from the textbook. So we'll just move on. So first problem is to find the equation for the bounding surface, set up a volume integral, and evaluate the integral to obtain a volume formula. And the geometry is a spherical cap with a radius r and a height h. So if we look at this is the sphere that we're looking at. This height is h, and we're interested in the volume contained within this spherical cap and this base that's here. This base is height h, but also you can write that as this distance, which would be r minus h. So since we're going to solve it in spherical coordinates, here are the transformation equations. And so we'll deal first of all with rho. So the expression for the upper surfaces is obtained by substituting these expressions for transformation into the equation for a sphere. Equation of a sphere is just this one that you see here. And if you make the substitution, you'll find that you end up with rho equals r, capital R, after some simplification. The expression for the lower surface is obtained by realizing that z equals r minus h, which is this height here. And that's equal to rho cosine phi. Don't forget the angle phi is with respect to the z-axis. So now we have basically this information which is given in terms of the variables in spherical coordinates. Rearranging this, we can express this as rho equals r minus h times secant phi. So now we have basically the upper bound for the surface and the lower bound. Next is to figure out the bounds on phi and theta. If we look at the intersection between the two surfaces, between these two, that will give you the upper bound on psi. So equating the two, that is r minus h sec phi with r, and solving for phi gives you cos inverse r minus h over h. So this is the upper bound on phi, and the lower bound will be phi equals 0. Phi equals 0, of course, will be with respect to the z-axis. And this angle here would end up being cosine inverse r minus h over h. The range from theta is just for the full circle. That's going all the way around. And so theta ranges from 0 to 2 pi. Putting it all together, we will have basically the differential volume, which from before is just going to be rho squared sine phi d rho d phi d theta. And this basically was obtained by computing the determinant of the Jacobian matrix. This is the lower surface, the upper surface, that is with respect to the variable rho. Phi ranges between 0 and cos inverse r minus h over h, and theta ranges between 0 and 2 pi. So now we have basically all the information we need to be able to populate the triple integral. And so that's all I've done here. So lower bound, upper bound on rho, lower bound, upper bound on phi, lower bound, upper bound on theta. And you can compute this integral and you'll end up with this answer. Now I've just made use of this integral. The first integral, when you integrate rho squared d rho, you'll end up with rho cubed over 3. And so out of that comes a sec cubed times a sine phi. So this basically is equivalent to 1/2 sec squared. Again, I don't expect you to remember things of this nature. If we ask you to do an integration like from beginning to end, and there are some complex functions involved, then we would give you an equation of such a nature. We don't expect you to derive it or memorize it. All right, so the picture for this basically can be accessed at this URL. And just to sort of make it clear that the top and bottom surface are the ones shaded in red. So here's the cap. Here's basically the flat surface. That was r minus h. And that's for the inner integral. For the middle integral, phi equals 0 corresponds to the yellow line. And the yellow cone would be the angle which basically is where the cap and the plane intersect. So that's this yellow cone. And then the half plane wedge that makes a full rotation outer integral. This goes full circle. This is basically associated with the angle theta. All right, let's do question 21. Triple integral. Problem is stated as follows. The volume between the sphere x squared plus y squared plus z squared equals 19. And the hyperboloid z squared minus y squared minus x squared equals 1. And z greater than 0. So we're looking at only at the upper hyperboloid. There is also a mirror image of it in the below the xy plane. So we're interested in the volume contained between this cap and this bowl, as you might say. So again, since we're going to solve the problem in spherical coordinates, here are the transformation equations. So we need to basically express the upper surface and the lower surface in spherical coordinates. So we just substitute the x and y and z into the equation for the sphere and equate, and we'll finally get rho equals square root of 19. For the lower surface, we basically make the same substitutions for x, y, and z into this equation, and we end up with this equation. And so this can be simplified using a trig identity. Cos squared minus sine squared is cosine 2 phi. And if we then solve for rho, we get this is equal to the square root of secant 2 phi. Because one goes into the denominator and 1 over cos is sec. The intersection between the two surfaces gives you the upper bound on phi. So if we equate this expression with this expression and simplify, so effectively cos 2 phi equals 2 cos squared phi minus 1 equals 119. So we've expanded cos 2 phi in terms of a trig identity. We would like it a phi value. This has got 2 phi, so this basically gets it into the situation we want it to be in, right? If you then take this and solve for phi, you'll get phi equals cos inverse root of 10 over root of 19. And the lower bound on phi will be 0. So phi equals 0 will be here, and phi equals cos inverse root 10 over 19 would be effectively this angle here. So phi equals 0. Phi equals cos inverse root 10 over root 19. The range of theta will again between 0 and 2 pi since you're doing a full revolution. So as before, the differential volume basically is this, and rho squared sine phi is the determinant of the Jacobian matrix. And so just taking this information, the blues and the yellows, and we have the limits on phi, the limits on rho, or bounds on rho, and the bound on theta, and so we can now put together the integral. And so this is what I've done here. Lower and upper bound on rho, lower and upper bound on phi, lower and upper bound on theta, and if you perform this integral, you'll end up with this expression. Now in this case, of course, when you integrate rho squared, you get a rho cubed, and so we'll end up with something that looks like this. And again, you can do this type of integral. I'm not expecting you to do it, but it turns out that it looks like this. Okay? All right, so we can visualize the different surfaces we're dealing with here. And so, for instance, red is the top and bottom surface for the inner integral. That's the bottom one and the top one. The yellow line and the yellow cone, there's the yellow line. That's at phi equals 0. And the cone would be phi at this value here. That's basically another two surfaces. And the third is the half plane wedge. that makes a full rotation. In other words, if you look at the slider T, right, if you basically let that run, this wedge will just make a full circle all the way around. So this next problem, taken also from chapter 16.5, question 81, is a more complicated triple integral. So the statement is one sphere is centered at the origin and has a radius capital R. Another sphere is centered at 0, 0, small r and has a radius of small r, where small r is greater than capital R divided by 2. What is the volume of the region common to the two spheres? So in drawing, it's easier to use just a trace to visualize the problem. So if you were to basically take a plane that basically cuts through the origin, in any particular direction, you will find that you will end up with a picture that looks like this. So the trace shows circle of radius r and another trace, another circle of radius small r offset by distance r along the z-axis. So from this image, it's very clear that in fact the region of interest is right in this region here. So you have the curve that you see here, and you have the curve that you see here. And we want to solve this problem in spherical coordinates. And so we make use of the transformations that allow us basically to express x, y, and z in terms of rho, theta, and phi. Now, in this problem, there's a bit of a problem because remember the rules for integration. We have to make sure that the boundaries are continuously differentiable. But if you were to look at rho here, rho would basically point to this contour as well as this contour. This contour is smooth, but the moment you reach this point, suddenly the direction changes. So at this point and this point, there's a discontinuity. Discontinuity as far as the derivative is concerned. And that means we have to break things up into regions. And the blue line basically is the dividing line between one region, which is above the blue line, and another region which is below the blue line. And so two integrals are required, and so we have to sort of be a little bit more careful in terms of how things are set up. All right, so that's the point that's made here. So for the upper surface integral, that's here, at the upper bound basically after substitution would be rho u equals r. So this is just the equation of a sphere, so rho u equals r. For the lower surface, we would use the cosine law. For triangles, r squared equals r squared plus rho l squared minus 2r rho l cos phi. Okay, cos phi basically being the angle in here, and we have an r that basically, this is a rho l, we have an r here, and we have an r here. And so you can express this length in terms of this length, and the angle between the two. And that actually is cosine phi. Anyway, if you simplify that, you get rho l equals 2r cosine phi. So the next thing to look at is what is the angle at which we could move from one region into another region? Well, that's determined by equating rho upper with rho lower and solving, which is what we're doing here, and then solving for phi, which then allows us to obtain the following result. Phi equals cos inverse capital R divided by 2r. So the lower bound, the lower bounds now in terms of, we've talked about the upper bounds for the upper surface integral, and for the lower bounds will just be rho u equals 0 and rho l equals 0. In this case, though, we have two different regions to consider. We know that the dividing line occurs at phi equals cosine inverse capital R over 2r. For this region, therefore, we go from phi equals 0 to phi equals cosine inverse r over capital R over 2r. And for the bottom region, we go from cosine inverse capital R over 2r to 90 degrees. That's pi over 2. So eventually, when we reach the point at the origin, we're basically pointing in this direction. So the angle phi, which is from here to here, would be 90 degrees. So that now allows us to set things up. Also recalling the differential volume, that this term here represents the determinant of the Jacobian matrix. So for integral 1, these are the bounds for phi, upper and lower. And for rho, these are the upper bounds, lower bound and upper bound for rho, and these are the lower and upper bound for theta. For integral 2, which is basically going to be the lower branch that's below the blue line. The limits on phi, or the bounds, are cosine inverse capital R over 2r. Lower and upper is pi over 2. And rho will be between 0 and 2r cos phi, and theta basically extends from 0 to 2 pi. So this more or less basically is the setup for the problem, and in the next slide basically we just have to do the necessary substitutions into the triple integrals, and then we can solve the problem. All right, so I just put the things together. Here's integral 1. Again, bounds on rho, bounds on phi, bounds on theta. And this is the second integral, bounds on rho, bounds on phi, bounds on theta. And if you simplify, you do the integral, you'll end up basically with this answer, which is consistent with the results we had when we solved using Cartesian coordinates as well as cylindrical coordinates. If you would like to look at a picture of this, you can. So for instance, the top surface, which is the inner integral, is red. Purple is the bottom surface, this integral 2. And so the third would be the yellow, which is a line and a cone, this one and this one. That's a middle integral of 1. And yellow cone and gray plane, so that cone and the gray plane, it's the middle integral for number of integral 2. And blue is the half plane wedge for both the integral 1 and integral 2. That's for the outermost integral. In both of the cases where we're dealing with the top surface and the bottom surface, the value of rho for the lower limits is going to be 0. So you see a 0 there, and you see a 0 there as well. So this is more or less basically how we have solved this problem. We had to split it into regions because the rho was basically not continuously differentiable. And so by splitting in two, we could make each section continuously differentiable. Well, that concludes lecture 16 and also this basically is completion of the first part of the course. Starting with lecture 17, we'll get into some new material. Anyway, thank you for listening.